इन सभी क्वेश्चंस को करने के लिए आप पहले तो एक सर्कल बना दो सर्कल बना दो एज्यूमिंग दैट मैग्नेटिक फील्ड इज प्रेजेंट एवरीवेयर. Hello students, in today's video we will discuss the concept of circular motion of charged particle in a uniform magnetic field. This is a topic which is pretty straightforward, but I find that students still struggle when they are asked to solve numerical questions. So they lack conceptual clarity, that is what I feel, and I will just try to emphasize on the most important concepts in this brief video. Let us assume that this blue region has a uniform magnetic field and the direction of magnetic field is perpendicular into the plane of the figure. Everywhere the magnetic field is into the plane of the figure, right? Now you have a charged particle, we will assume a positively charged particle having charge q and mass m, and that particular particle is projected in this plane of the diagram. So the magnetic field is into the plane of the board and we are projecting the particle somewhere on the plane of the board. That means velocity is directed in the plane of the board. So this is the charged particle having mass m and charge q, and it has been given some velocity v in this magnetic field. What will happen? As soon as charged particle is projected, it starts experiencing a magnetic force. Now what is the direction of magnetic force in this particular case? The direction of magnetic force is always in the direction of v cross b. In fact, the force is q_v cross b. This is what you have studied. So what is v cross b? How to figure out v cross b? First thing, force is perpendicular to b, magnetic field b. So b is perpendicular to plane of the figure means force is somewhere in the plane of the diagram. Force is somewhere in the plane of the diagram and force is also perpendicular to velocity. So force is either this way or it is this way. We just need to figure out whether the force is directed this way or this way. As soon as the charge leaves our hand, it is moving with velocity v in magnetic field b, it experiences a force and the magnetic force is directed in the direction of vector v cross b. So in this particular diagram, this is vector v and b is going into the plane of the board. So you just somehow need to find out what is the direction of v cross b. For that, please follow my steps. The force is perpendicular to b, therefore force is in plane of figure. Force is perpendicular to v, therefore force is perpendicular to this red line. Now you just need to figure out whether it is this way or this way. For that, this is v. Stretch your right hand fingers in the direction of v. Try to curl them in the direction of magnetic field b. Thumb is pointing somewhere upward. So it clearly means that the force is going to be perpendicular to the velocity vector in this direction. The direction in which this force is pointing is actually the direction of it is the radius of the circle on which the particle is going to move. So the center of the circle is going to lie somewhere on this line. Therefore, you must have been able to figure out that the circular path of the particle will be somewhat like this. Yes. Had it been a negatively charged particle, assume that it is a negatively charged particle, in that case the direction of force will reverse. If this q is negative, then force will be directed in the direction of vector minus v cross b. So you need to do v cross b and reverse it. So if you project a negatively charged particle from this point in the same magnetic field, then it will take a path like this. It will go in circular path like this, because in that case the force is directed this way and somewhere here you will have the center of the circle. So the particle will begin to move in clockwise direction. Right now, if it is positively charged particle, it will go in anti-clockwise direction. So please try to understand, doesn't matter at which point you have projected the particle. If you have projected the particle here with speed v, it will move on the same circle. If you have projected the particle at this point with speed v in this direction, it will move on the same circle. If you have somewhere projected the particle here with velocity v, it will move on the same circle, because in every case you can convince yourself that the force vector will be directed towards one common point, that is the center of the circle. So, in this case all of you understand that radius of the circular path is given by mv by qb and time period of circular motion is given by 2 pi m by qb. This is quite common knowledge. Now, what happens if you have magnetic field in everywhere perpendicular to the plane of the figure? This blue region everywhere shows magnetic field is perpendicular to plane of the figure, into the plane of the figure. This is what I am assuming. So, if the magnetic field exists everywhere and you project a particle in this plane surface in any direction, just as I illustrated in the previous slide, you project the particle in any direction in this plane, it will move in a circular path, right. So, if you project a particle from here, it is going to move in a circular path. This will be the circle, as we have understood. But what will be the case if the magnetic field does not exist everywhere? For example, if the magnetic field is only existing in the blue region, nowhere else, only in the blue region, then what will happen to the particle? So, once you have projected the particle from this particular point in this particular direction, the particle does not know that it is not going to see any magnetic field after some time. It will just move as if there is magnetic field everywhere. So, if you have projected this particle from this point in this particular direction perpendicular to velocity, this is radius of the circle, and somewhere here we have the center of the circle, right. So, particle begins to move in circular path. If it is a positively charged particle, magnetic field is inward, as we have seen, it will go in anti-clockwise sense. So, the particle starts moving. Now, it does not know that there is no magnetic field after it completes half the circle. So, it is going in circle, 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 it reaches this point. At this particular point, its velocity is directed towards left. In magnetic field, force is always perpendicular to velocity. So, power of the force is always 0. Magnetic force will not perform any work on this moving charge. Therefore, kinetic energy, that is speed of the particle, never changes. So, if it is 10 meter per second, here also it is 10 meter per second. Only thing that has happened is direction of velocity has changed. So, the particle will continue to move on this circular path, but when it reaches this point, all of a sudden the magnetic force is switched off. In this white part of the diagram, there is no magnetic field. So, if the velocity of the particle is right now v and it does not experience any force, its velocity is not going to change. So, it will continue to move in a straight line in this particular direction. So, what do we see? We see that the direction of motion has deflected by 180 degree in this case. Remember, direction of motion has changed, velocity has changed, momentum has changed because the particle experienced some force, but its kinetic energy has not changed because the force that was acting, the magnetic force, it has not performed any work. Momentum has changed because there was a force acting on it. This force has got some impulse, but the fact is that the force was not able to do any work, and therefore the kinetic energy has not changed. Okay. So, we have understood that if everywhere we have magnetic field, the particle is moving in a circle. If this is the situation that half of my circular zone has magnetic field, that means you have projected the particle from this point, it will go in a semicircle and it will exit the magnetic field. How long the particle has remained inside the magnetic field? Very simple. The time period of the complete circular motion is 2 pi m by qb. So, half of this time has been spent inside the magnetic field. I remind once again that this is just an indicative circle. Particle is not going to move in circle here. It entered into the magnetic field here and it exits from this point. This is the semicircle that it has completed. This dotted circle is just an indicative circle. Just to make my diagram clear, it has got no other purpose. Now, what will happen if this magnetic field does not exist up to this point? You all can understand that if this magnetic field exists up to this point or this point or this point or this point, particle is going to move in semicircular path. Even if the magnetic field is existent just up to this point, it will be able to go in semicircular path. But what happens if magnetic field is limited to a very narrow zone? If this is the case, then of course particle is going to move in semicircle. But what happens if the magnetic field is only limited to a very narrow zone? I mean, you have projected the particle from this point with some velocity v, charge is q, mass is m, and let us say this region has width d and d is less than mv by qb. What is mv by qb? mv by qb is the radius of the circular path on which this particle is going to move. So, if the width of the magnetic field region is less than radius, what does it mean? It simply means that particle is never going to reach this point, because this is the radius. So, if magnetic field exists in a region that is narrower than this radius, then obviously particle is never going to reach this point, isn't it? So, this is the same situation that I want to discuss. D is less than mv by qb, d is less than radius of the circular path taken by the particle. Magnetic field is inward, its strength is B. You have projected a charge somewhere here. Had there been magnetic field everywhere, it would have gone in a circular path like this. तो इन सभी क्वेश्चंस को करने के लिए आप पहले तो एक सर्कल बना दो. सर्कल बना दो assuming that magnetic field is present everywhere. So at this particular point, as soon as the particle enters into the magnetic field, its path becomes circular. So this velocity is tangential to circle. Perpendicular to this, we have got radius of the circle, and somewhere here we have the center of the circle. This is the situation. So particle starts to move on this circular track. It goes on this circular track till this point. Beyond this, it does not experience any magnetic force. When it reaches this point, it has a velocity directed like this, and beyond this there is no magnetic force, so it will just move in a straight line. Again, this dotted circle is just an indicative circle. The particle has moved on this circular path only from this point to this point, no more than that. So the overall effect is that particle moved over an arc of a circle and it got deviated. There is some deflection in its path. What is the deflection? The answer is very simple. The deflection angle is this angle only. You can see yourself. This is the direction of initial velocity of the particle. This is the direction of final velocity of the particle. That means a tangent at this point is the direction of final velocity of this particle, and deviation angle of its velocity is this angle. Earlier the particle was going like this. If there were no magnetic field, it would have moved in this direction only, but because of presence of magnetic field, it got deviated and now it is moving in this direction. So the angle by which it has deviated is this angle. It is very easy to see that this angle is same as this angle, because this is 90, this is 90, so this becomes 180. In this quadrilateral, this is 180, so sum of these two angles is 180. So this angle is 180 minus theta, therefore this is theta. You can work it out yourself. So by what angle the particle has got deviated? Answer is this angle theta, and it is very easy to write, because this width is d and this is the radius of the circular path taken by the particle. Though the particle has only moved on a part of the circle, but okay, this is the radius which is given by mv by qb. So just looking at this diagram, you can see that sine theta is equal to d by r. Sine theta is d upon r. So the particle has deviated itself by this angle, isn't it? Where r stands for mv by qb. So if the region of magnetic field has got width which is less than radius, then this is the amount of deviation that has been suffered by the particle. Its momentum has changed because its direction of velocity has changed, but again its speed will never change, because magnetic force does not perform any work. The force is always perpendicular to the direction of motion. Such a force will never perform any work. So no work done, no change in kinetic energy, but this force has some impulse, and therefore there is change in momentum. So velocity changes, direction changes. Next, you can encounter a situation like this. Suppose this is the region in which you have a magnetic field into the plane of the board, and somebody says that a particle has been projected at this particular point into the magnetic field. Let us say just for sake of example, let us say this angle is 45 degree. That means this direction of velocity makes an angle of 45 degree with this particular direction, the edge of the region of where the magnetic field starts. So if a particle of charge q and mass m, q is positive, has been projected like this into this magnetic field region, what kind of path is it going to have? Again, you students, you must realize that in all cases, as I have been repeatedly saying, in all such cases the particle's path is going to be circular only. If you project it from here with speed v, it is moving on this circle. If you project it from here on this, in this direction with speed v, it is moving on the same circle. It is moving on the same circle. So you just need to realize that in the present question, the magnetic field starts from this line. The magnetic field is to the right of this red line, and to the left of this line there is no magnetic field. That's all. That is the only difference. That is the only difference. In this particular question, the magnetic field was present in the half of the circular path. In this particular question, magnetic field was present to a very small segment of the circular path, and in this particular question, the magnetic field is again present only to a segment, only on the segment of the entire circle. So if there were magnetic field everywhere into the plane of the board, then particle will again go in circular path like this. Always draw this indicative circle, always draw this indicative circle. Whenever the velocity of charged particle is perpendicular to magnetic field, the path is circular. It may be part of a circle, but it is circular. So just first assume that there is magnetic field everywhere, draw a circle, draw a circle. That is one tip that I can give you. So draw a circle. Now try to figure out where from this particle has been projected on this circle. Now if the question is saying that, this is the magnetic field region and this is how particle has been projected, you need to understand that particle has not been projected at this point. I mean, if this is the circular path, then velocity here is horizontal. But at the instant particle enters into the magnetic field, its velocity is not horizontal. So when it is entering into the magnetic field, it is entering somewhere here, where the velocity is making an angle of 45 degree with vertical line. So just by looking at the diagram carefully, one can understand that okay, had there been magnetic field everywhere, this would have been the circular path, but the magnetic field starts from this particular point where from the particle has been projected. Particle has been projected in this particular direction, so it will only cover a part of the circle inside the magnetic field. So initial velocity, as soon as you leave the particle, as soon as the particle is released inside the magnetic field, it begins to move in circular path. So this red arrow is actually tangent to circle, which means the radius of the circle is perpendicular to this. So radius of the circle is somewhere like this. This is the center of the circle. I hope you understand. So this is the center of the circle. Now it is going in circular arc like this. At this particular point, again it finds that magnetic force has been switched off. Therefore, it will continue to move along that red line after that particular point. It is very easy to figure out that, see, this is the radius, this is the radius. So this particular triangle, if I complete a triangle like this, this particular triangle is at least isosceles triangle because these two sides are of same length. So if this is 45, this is 45. So this has to be 45. Can you understand that? So this is 45 and this is tangent, this is radius, this is 90. So this angle is again 45 degree. So you can figure out this angle is also 45 degree. So in this particular case, the path, the entry point and exit point, they are quite symmetrical as far as their direction is concerned with respect to the magnetic field. Both the angles are 45 degree. That is what I want to say basically. Don't understand anything apart from that. So it is very easy to see that this particular angle is 90 degree. So what has happened? This particle has covered 1/4 of the circle inside the magnetic field. It has entered into the magnetic field like this, and now it is exiting the magnetic field at this point. It has only moved through 1/4 of a circle inside the magnetic field. So how much time it has spent inside the magnetic field? 2 pi m by QB is the time period, 1/4 of this. So there is time spent by the particle inside the magnetic field. Then another class of problem which disturbs you, again let us assume that this blue region is a magnetic field. Magnetic field is directed into the plane of the figure. This is x direction, this is y direction. Magnetic field is obviously in negative z direction, right? And a particle of mass m and positive charge q is projected with some velocity v along y direction. So, in words, the question might say that the magnetic field is minus b0 k cap. Okay, it means that magnetic field is in negative z direction, its strength is b0, and the initial velocity of the particle is something v0 or v j cap. So, initial velocity is in y direction and the particle has been projected from origin into the magnetic field. Now, the question may ask you to write the velocity of the particle as a function of time or its position as a function of time. Velocity or position as a function of time. Now, because velocity is perpendicular to plane of the magnet to the direction of magnetic field, particle will take a circular path beyond doubt. Now, where is the center of the circle? Again, figure it out. V cross B, B is inward. V की तरफ हाथ को फैलाइए, B की तरफ उंगलियों को घुमाइए. ये V क्रॉस B का डायरेक्शन है, अंगूठा इधर फोर्स लग रहा है, सर्कल का सेंटर यहाँ कहीं होगा. तो नेचुरली ये पार्टिकल यहाँ से एक सर्कल में घूमने जा रहा है जो कुछ इस तरह का होगा. ये सर्कल का सेंटर पॉइंट है, ये ऑरिजिन है, इसलिए सर्कल के सेंटर को C लिख रहा हूँ. ऐसा C लिख दिया मैंने सर्कल के सेंटर को. ये रेडियस R है, राइट. नाउ वी ऑल नो दैट टाइम पीरियड इज 2 pi m by qb, or you must understand that angular speed is 2 pi by t. Angular speed is radian per second. That is simply given by qb by m. So, basically the particle starts to rotate in this circle with an angular speed of qb by m, so many radians per second. So, after time t, the particle will rotate through an angle theta, and that theta is given by omega into t, where omega is this number. So, particle begins to move in this circle, and in time t it will rotate through an angle that is given by omega into t. So, particle will be somewhere here after time t, right. So, if somebody asks you write velocity vector in I cap j cap notation using unit vector I cap j cap at time t, it is very simple. The magnitude of velocity is still very much v, only thing its direction has deviated. So, what you need to do is you just need to write its two components, right. You can easily see that if this angle is theta, this is 90 minus theta, this is theta. So, v cos theta and v sin theta. So, we can write velocity as v cos theta I cap, j cap. So, sorry, v cos theta is the y component, v cos theta j cap. So, in place of theta, we will basically write omega t. Omega is qb by. So, in place of theta, we should write this. The y component of velocity is this, and the x component of velocity is minus v sin theta I cap. So, this is how you can write velocity as a function of time. This velocity in function of time only, because theta is dependent on time. Similarly, if somebody asks you what is position coordinate of the particle at time t, तो आपको इस पॉइंट का x और y कोऑर्डिनेट लिखना है, just by observation, nothing else. So, you can see this is radius and this is r cos theta, this is r cos theta, this is again radius, this is r cos theta. So, x coordinate of the particle is this length only. So, r minus r cos theta with a negative sign, negative because this is negative x coordinate, isn't it? This is negative x direction. So, if this is 2 meter, we will write x coordinate as minus 2 meters. So, again theta should be written like that. So, this gives you x coordinate, and similarly you can write y coordinate. Y coordinate is nothing but r sin theta. So, here you get the position coordinate of the particle as well as velocity of the particle in unit vector notations. So, I think I have given you all the fundamentals, necessary fundamentals for dealing with questions where a charged particle is moving perpendicular to magnetic field in a circular path. So, students, I hope you like this video. If you really liked it, please share it with your friends and do not forget to like it, at least like it. See you in the next video with some more concepts, some more questions. Goodbye.